Welcome to qnawire.
We're told the family of bell-shaped curves are described by this function, and this is called the normal density function. And there's two constants. We have a mu, which describes the mean, and we have another constant called the sigma, and that tells us the standard deviations. And we're going to be looking at the case where mu is equal to 0, giving us this more simple function. And we're being asked about a couple of things. So we're being told to find the asymptote, maximum value inflection point. So let's go ahead and start. So to find the asymptote of this function, we're looking for when x goes to positive or negative infinity. And so if you look at this function, it's e to the minus x squared over 2 sigma squared. So this can be rewritten as y equals 1 over e to the x squared over 2 sigma squared. So over 2 sigma squared. So if you look at this, as x goes to really big numbers, so let's say e to the 100 over 2 sigma squared, and sigma is still positive, so it's going to be e to the 100 or e to the, you get 1 over a really big number, so you get 1 over infinity. Well, that's just really like, it gets closer to 0. So, and since exponential functions, since it's being squared, it doesn't matter if it's going to positive or negative infinity, it will still go approach to 0. So it will have a horizontal asymptote at y equals 0. And then we're being asked to find the maximum value. So this means by taking the first derivative. So if we take the first derivative, we get f prime of x, and it comes out to be minus e negative x squared over 2 sigma squared times 2x, so this is times 2x over 2 sigma squared. And you set this equal to 0, and you can see that this will never equal 0. So if you plug in x equals 0, you get 0. So you get x equals 0, and if you plug in f of 0, you get 1. So we have a local max at 1. And in this case, it is the absolute max too. And then we're told to find the inflection point. It involves taking the second derivative. And this is a bit more work. So this is going to come out to be minus e to the minus x squared over 2 sigma squared, that's a sigma, times 1 over sigma squared plus x over sigma squared times e to the minus x squared, that's squared, over 2 sigma squared times 2x over 2 sigma squared. And then you can pull out a common factor of e to the minus x squared, so you get e to the minus x squared over 2 sigma squared. And you can also pull out a factor of sigma to the 4th, and then you'll get x squared minus sigma squared equals 0. And you can't this cannot equal 0, so we said x squared minus sigma squared equals 0, so this gives us x squared equals sigma squared. Take the square root, you get x equals plus or minus sigma. So that's the inflection point. And then we're being asked to evaluate what role does sigma play in the shape of our curve. So if you look at this function again, so we had, remember the function was y equals 1 over e to the x squared over 2 sigma squared. And it's being asked to look at how sigma plays a role. So as sigma, as the value of sigma gets closer to 0, as this number gets really close to 0, you get x squared. A reminder, I'm just writing at the exponent, so x squared over 2 sigma squared. So as the denominator gets really, really small, you get a really, really big number. So as sigma approaches 0, you get big number. So you get a really, 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 really big number. And in fact, it actually goes really, really close to infinity. So you get 1 over e to the infinity again. So you get 1 over e to infinity. And remember, 1 over a really big number approaches 0. So as sigma gets close to 0, what's happening to y is that y is approaching 0. So sigma goes to 0, y approaches y is also getting closer and closer to 0. And so what happens is this makes this the function itself gets a lot closer to the y-axis. So it becomes more and more narrow and more closer and compacted together. And and for vice versa, so as sigma approaches as sigma gets bigger, so let's just say as sigma goes to infinity, let's just say sigma goes to infinity, x squared over 2 sigma squared, well, what happens to this? So sigma squared goes to a really, really, really big number. So you get x squared over sigma squared, and this approaches 0. And then you get and it approaches 0. And so what's happening to it, it's the opposite is going to happen. So as sigma goes closer and closer, y actually approaches 1. And this will become a bit more clear when I show the graph. So I actually have taken the liberty of drawing some of the functions before. So as you can see, the green curve right here is minus x squared over 4. So if I increase it, so let's say I increase it to 16, this purple graph shows that it's much more widespread and much more further out, which is what we predicted. And as I get closer and closer to a smaller number, the denominator, you get a more sophisticated, more compacted graph. And that's exactly what we predicted.